In number 5, liquid hexane is completely combusted to produce carbon dioxide and water. Here's the unbalanced equation. First, you have to balance the equation, balance the carbons first, the hydrogen second. You'll notice when you add those together, you get 19.5, so you need 9.5 oxygens right here to balance that. It's recommended that you always balance these carbon, hydrogen, and oxygen. That's alphabetically, in alphabetical order. Next, you want to find the delta H for the hexane. This is the hexane right here, and it would be products minus reactants. And this is the overall enthalpy of the reaction. Notice it's negative because it's energy released. Plugging this into an equation, we now have this, and here is the enthalpy of the product, carbon dioxide, the enthalpy of the product, water. Notice it's multiplied by 6 and 7, the constituent molar coefficients, and then this is the hexane right here, and oxygen of course is in the reaction, but it's 0 because it's in its standard state. Doing the algebra, I think these add up to these, and this is the x value, and trusting my math, which you might not want to do, I believe I ended up with the enthalpy of 248.4 kilojoules for the hexane. In part D, it asks you to that there is a 0.036 mole sample of hexane that's combusted in the calorimeter. Calculate the amount of heat released. So we take the 0.036 moles, and there are 4 times 10 to the third kilojoules released per mole. Multiply those two together, and you'd have the amount of kilojoules released. Letter B, don't do. It's not a type of question that's asked on the AP or the college exam anymore. In number 6, it says determine the combustion of carbon monoxide, or the combustion of carbon monoxide is listed above. Determine the standard enthalpy change for the combustion. And for this one, you would need to take and manipulate these two reactions to give you the top reaction right here. And so the first one, CO would have to be reversed to become CO goes to C solid plus 1/2 O2. And when you do that, the enthalpy sign has to be reversed to become positive 110.5. The second reaction remains the same. C plus O2 goes to CO2. The enthalpy remains the same because you didn't change anything. That's negative 393. And then you can add the two reactions together. The carbons cancel with the carbons. We lose a 1/2 mole of oxygen here, and you end with a 1/2 mole of oxygen left. And CO plus O2. 1/2 O2 goes to CO2. When you do that, you add the two enthalpies together as well, and you end up with a delta H for the reaction of negative 283 kilojoules per mole. Lastly, turning the page, a long story problem where a lab similar to one that we did in class is performed. Both solutions are at the same temperature. Give appropriate units. First of all, the equation that you'll be using is Q equals mc delta T. The units on that are joules, grams, joules per gram Celsius or Kelvin, and then Kelvin or Celsius. And then letter B, measure list the measurements. You'll need the mass of each solution in grams, the initial temperature of each solution, and the final temperature after they're mixed, so you can calculate the temperature change. In letter C, explain how to calculate the following. First of all, use the molarity triangle to find the number of moles of each of these. Since they're equal, they'll have the same number of moles. Tells you that in the problem. And it'll be a 1-to-1 ratio for the water that's produced. And so whatever the number of moles of either of these is your moles of H2O because it's a 1-to-1 ratio. And then in part 2, take the number of joules that are produced that you calculated up here and then divide it by your moles of water that are produced. Since it's called the enthalpy of neutralization, what they'll want to know is the joules per mole of the neutralized substance that's produced. Since they're all equal, it doesn't matter which moles you use, just use the moles that's most convenient. In letter D, it says it's repeated with 2 molar. Since there's more stuff, more energy will be produced. There'll be a greater energy given off, greater temperature change as well. And then state whether the molar enthalpy of neutralization will change. That will stay the same since it's a ratio of energy per moles. The ratio would be the same since you're dividing a larger number by a larger number. Suppose a significant amount of heat were lost during the experiment. What effect would this have on the calculated value of the molar enthalpy? Well, it probably technically would just lower the amount of energy right here, and then your moles would still be the same, so you would have a smaller ratio because you have a smaller number on the top.